To this second session of the workshop on surrogate models for European systems. Our next speaker is Michael Goldstein, who will speak on emulation for model discrepancy.
Hi, so thanks for inviting me. Very happy to be here. So my topic, so I was at the first workshop. I appear to be at all the other workshops as well, and so I thought the workshops were great. Uncertainty quantification, it covered virtually everything. The only thing I thought was possibly missing was uncertainty quantification for models compared to uncertainty quantification for the world, but I was told that the idea was this was going to be so baked in that having a workshop would be kind of irrelevant. Okay, so I'm going to bake this into my talk. Okay, so I'm going to talk about model discrepancy, relation between the models and the world. Because this is a surrogate model session, I'm going to show how surrogate models or emulators are relevant to doing this. Okay? So maybe a bit of pardon me, personal perspective on this. Okay, so I got involved and interested in this maybe in the early 90s. Okay, so I just moved to Durham. Okay, and one of my colleagues, Alan Schwelt, was working on okay, so he had a friend, Bob Parrish, who was a consultant in the oil industry, and they were concerned with, well, in the oil industry, they have a particular kind of problem called history matching, okay, which is where I snuck the name from, for what many of the things that I do. So you have an oil reservoir, you want to manage it, you build a simulator for that. The simulator describes the permeabilities, the porosities, the fault structure, and then it uses things like Darcy's laws to explain if you do various things at wells, what will actually happen. So before you're allowed to use that to asset manage, the first job is what's called history matching. So history matching is to find an identification of the reservoir geology such that when you run the reservoir using the methods that were used over the historical period, what you see at the wells matches what people actually saw at the wells. Okay? So that is an important step. Whether you want to find one match or, as we now like to think about it, finding all the matches, is quite a hard task. So the reservoir engineers, I mean really they wanted to leap on planes and go out to the Middle East and negotiate complicated contracts and do exciting things. But what they spent much of their time doing was sitting there with these slow, stubborn simulators and saying, well, maybe if we push those permeabilities up and put that fault in, it would match better. Several hours later, they'd run, oh, it doesn't seem to have, so they'd do something else. And so it was very much a slow and stubborn thing. Okay? So Bob asked Alan, surely this is a bit like a stats problem. Could you write a stats routine that will do this? So Alan said, fine. So he wrote a program to do this. Now this was old school, so I think the program was in APL. So it was probably 3 lines of code, one of which was a comment. Actually, I'm joking, you would never put a comment in a beautiful cryptic piece of APL code. But anyway, so the point is, yeah, so we had a method, and of course, and so it was clear, interesting, and as we talked about it, virtually all of the problems that come up in, effectively in UQ, sort of were raised. So it seemed an interesting test bed to develop things. Okay? So with various colleagues we did this. We spent a lot of time thinking about how you would history match oil reservoirs and extended the methodology. Okay? And virtually the first thing we wanted to do was saying, okay, we want to history match the reservoir. What counts as an acceptable match? Or maybe I could use the board, okay, rather than waving my hands. Okay, so here's a typical kind of data you might want to match. So here's a particular well, here's time, here's pressure. Okay. So the pressure profile drops over time, one of the reasons that wells stop doing stuff. So maybe the observed pressure profile was like that. Okay, so that's true, well, observed. Okay. And so what we want to do is to create a geology such that when you run the simulator, it does effectively that. So here are 2 possible curves you might get. Here's curve number 1, and here's curve number, that's run 1, And here's another curve. Whoops. And that's run 2. And it could be that run 1 on average is a bit closer, but they would still prefer run 2 as a match. Partly because it's kind of easier to push this out. If you think what's going to happen next, well, you just go down the curve and you just keep on correcting it. But partly because they could understand it. Okay? The reason that there would be a fairly constant offset would be to do with features that they understood. For example, when you make a model of a reservoir, it's on a grid, and the wells, certainly at that time, probably still now, need to move to the center of the grid squares, so the wells actually move a bit, so the times when things happen aren't exactly time, so the notion of an offset seemed perfectly plausible to them. Okay? So there were 2 features of the match. Feature 1, okay, you should think about the level at which it might be wrong. So they'd have been very suspicious if they got it exactly right, because the wells are in the wrong places. Point 2, okay, is effectively it's the correlation structure that they're looking at. At an individual point, then up and down, any one of them could be a good match. It's the correlation of the discrepancy across time, or across everything you're interested in, that effectively distinguishes a good match from a bad match. Okay. So those are the kind of things that effectively we're carrying in our minds to try and do. Okay. So, models from physical systems. UQ is a huge area, but any subject will be, any large scientific subject will be addressed by a model, and that model will raise big UQ issues. There's all reservoirs at the top, natural hazards, disease modeling, energy planning, climate change, galaxy formation. These are big, complex problems. All of them scientifically are very different. The underlying methodology for quantifying uncertainty could be argued to be the same. I mean, I argue it to be the same because I did the same things when I did each one of these things, and the scientists seemed happy to go along with that. Okay, so let's talk about this. Okay, so the first thing is, analyzing in the models are great. What does that say about the world? So we need to be careful in our use of uncertainty statements to go from the models to the world. So this talk is about high-level principles for doing this. So before we start, if it's a statement about the real world, it should be clear what that statement means. So is an uncertainty statement a property of the world? If so, what property is it? Is it the judgment of an individual? If so, who? Does it mean something else? If so, what? Okay, well, different people may have different answers. My answer is simply, what I do is that all statements of uncertainty are the judgments of individuals. Okay? So not the probability of an event, the probability of a catastrophe, the probability of rapid climate change, but my probability or your probability, which may differ, and if they differ, we should look at why they differ. And again, even though I'm very wedded to this, you may have a different view, and the only thing I would ask is you state clearly what your view is and what your statements mean. Okay, so the Bayesian approach follows from the subjective approach. Okay, it gives you systematic tools for combining all your uncertainties, and it's widely used and successful. I think probably during the week we'll probably see widely used successful Bayesian methods being widely used successfully. Okay, let me just say I'm going to have a couple of slides here before I go on to say I take a slightly different path, because the Bayesian approach is hard as the problems get large and complex, because complex problems are hard, and the Bayesian approach is actually quite grueling in the sense that you need to specify so many probabilities and then do such a delicate analysis that it can be off-putting to do this. So obviously 1 is unavoidable. How about 2? So I use what's called Bayes linear methods. I advocate them. So in Bayes linear methods you replace probability, which is quite a crude method of specifying beliefs, in the sense you have to specify everything before you can get to the things you want, by going to expectation as my primitive. Okay? And if you are interested in that, so Dave Finetti, who's probably the deepest thinker on uncertainty, sort of wrote his summation of his life's work called The Theory of Probability. If you read it, it's actually a theory of expectation for effectively this reason. I think he called it The Theory of Probability because it wouldn't have been a multi-million bestseller if he called it The Theory of Expectation, so he went for the commercially viable title. Anyway, okay, so we specify directly the collection of means, variances and covariances, and higher moments if we want them, and probabilities, they're just expectations of indicator functions that you're willing and able to do. You put them in and then you apply our methods. Okay, so this leads us to Bayes' linear methodology. Linear because expectation is linear. There's a book about it. There's a much shorter sort of quick reference in StatsRef Online. So it's similar in spirit, I explain to people, to a full Bayes analysis, but it uses a simpler approach for specification and analysis, and you can either view it as an approximation to full Bayes if you would have liked to do full Bayes but you were a bit overwhelmed by complexity, or the appropriate analysis using a partial specification. I'm just going to put the equations up. Bayes' theory works off one equation, Bayes' theorem. Bayes' linear theory works off two equations. How I update my expectation for a vector given observation of another vector, and how I update the variance. These are linear fitting arguments. Why they are appropriate, you'll recognize them because you probably use them many times yourselves, certainly if you're a statistician. Why they are appropriate, obviously, is a complicated question. The book will go into some detail about that. And of course, once we start stepping away from things that we're traditionally trained to do, we need to think about the fundamental reasons for doing things. So what I would say is that the Bayes approach is great as a model. And what is it a model for? For perfectly rational individuals who live in small worlds where everything is sort of set out up front and accounted for. It's a model, therefore it needs to be related to actual inferences of real people in our actual world. And the Bayes linear approach does give us tools to do this. And when I put this up, you can see that in fact, it's just like the statement I made about models originally. Models are great, but you need to think about their relation to the real world, and the Bayes linear approach gives us steps to do that, which I'm not going to talk about. I'm just going to explain, therefore, that I'm not going to spend much time talking about calculations because the computations are not particularly hard. It's setting things up so that those are good computations that's a challenge. Okay, so the limitations of model-based analysis. So any model basically tells you how the system properties, the inputs, affect system behavior, sort of the outputs. We simplify twice. We simplify the properties of the system because they're complicated and we don't know them. We simplify the rules for going from properties to behavior, partly because the math is too hard, partly because we don't fully understand the physics anyway. And that's fine. And that's why models are useful. If we had to do the full complexity of the world, we would never do anything, provided we remember that we've made these simplifications and we don't confuse having done the model and doing wonderful things with actually having sort of assessed uncertainties in the world. Okay. So the questions we can raise are, okay, we've done an analysis of the world. So we have a simulator. We analyze the simulator. What does it tell us about the real world system values? So the simplest possible thing you can say is you ask the expert, you say, okay, how close do you think that the model is going to be to the world if you got it as right as you could possibly make it? And they say something like plus or minus 10%. So you add a 10% extra error on. Okay? And clearly it's much better to do that than to pretend that the model got it exactly right. It's a far more sort of useful statement to make. It starts to make the bridge between the model and the world. Okay? And often we do that. Okay? So this whole idea of treating the discrepancy as independent of the simulator and of X star. So in other words, if I run the simulator at the best value, then is this just an error I've made of plus or minus, say, sort of 10%? Yeah? Okay, but there are questions obviously that are raised that we want to get into. So is X star the actual system properties? And why should the actual system properties be the best fit for our imperfect model, for example, on climate models, you have water in its behavior, you know, I mean, it used to be tar or something, now it's treacle, you know. You don't put water in as water because at the scale of your computations, your model just, you know, would not create the phenomena you want to create. Once you get away from the notion that these things are true things, are there best inputs? And what does an expert judgment about a best input actually mean? Okay, and the thing that really threw me was I came from these oil reservoir models and trying to get, so I would have a model at a certain level of simplification, and I would say add 10%, and then I'd say, but next year I'm going to be able to build a better model because everything's restricted by runtime. I'm going to half the size, my grid size, okay, and then that model will be plus or minus 5%. But what about the difference between the two models? The difference between those two models seemed highly X-generated, so I could not create a belief specification that corresponded to what I thought based on this notion. So if you're not going to go very carefully, just adding 10%, brilliant, much better than not doing it. I don't want to put anyone off doing that, but structural discrepancy should take us a lot deeper. Okay? So we're now going to talk about systematic ways of actually doing this. Okay? So obviously there are many, it's such a huge subject, how does a model differ from reality? You know, well, philosophers think about it a lot, we think about it a lot, blah, blah. Yeah, okay. Now, I think, the way I cut this is to say that basically I view pragmatically you should think of two different kinds of discrepancy. Firstly, what I call internal discrepancy. So that's the aspects of structural discrepancy that you can discover by experiments on the computer model itself. Okay? So these are things that the experiments that we can propose, we can do them, we learn from that aspects of discrepancy, and effectively people will buy into that because you know, that was the argument that was made. So we'll talk about that, and so that's clean and it's very sort of useful and important. It can only take you so far though, because if there are, for example, missing physical processes, there's no operation on the model, on the simulator that can actually take you there. So the second part is our external discrepancy. So that's, we need to have expert judgment, statistical estimation and stuff. Okay? So I want to, if I can do it quickly enough, discuss two examples which illustrate various features. One example for internal and one for external, which are going to introduce surrogate models for doing this. Okay, so internal discrepancy. Any aspect of discrepancy we can assess by direct experiments on the computer. What might that be? For example, here's some. We may have a forcing function. That forcing function, usually we run the model as if we knew what it was, but really we don't, so we can perturb it. There's a state vector maybe that we push along. We're acting as if that state vector exactly pushed by our equations. Really we know that it doesn't quite, so we could add a bit of noise to that. We have parameters that we fix over space and time, maybe. Most models do. We can allow those models parameters to slowly vary. And so we can do things where the modeler says, yes, if I could only do this properly, that would be a better representation of my uncertainty. So we carry out experiments, we do all of these random things, we vary parameters, we vary all these things. So we fix a set of input parameters for the model as we would run it. We do a whole bunch of variations of the experiment that we do. And that allows us basically to understand what the variance is of the internal discrepancy variance is for an individual choice of input. So for some inputs, we know what the discrepancy variance is, and what we then do, and this is where we use our surrogate function, we need to extend that to all the other x's, and we do that by, here's this word emulation, okay, and so we're going to do experiments, and then we're going to emulate. And whether this is easy or hard to do depends on whether the person who built the model understands that the model is meant to help us understand the world. And so therefore they could think, what would make it easy to do the experiments? So they can make it easy for you or they can make it hard for you. The more people understand that you can do this, they may help to encourage modelers to actually to make it easy and therefore to make these things practical. And I've encountered many models. Sometimes it's dead easy, other times it's not worth the effort. Okay? And that's because of how they're coded. So let's do our first example. So this is on the water cycle. We're going to talk about a rainfall runoff model. So that everything I know about this is taken from one page on Wikipedia. Okay, so there's evaporation and transpiration for moisture leaving. It goes into the ground, it runs off, and rain dries it. So this is the water cycle. Okay, and so floods happen when effectively there's lots of runoff. Okay? So the models we're going to use are what's called FUSE, the framework for understanding structural errors. So there's two ways you could imagine doing flood modelling. You could say, look, here is a bit of the Thames that comes in just by a nice bit of London. We need to really understand this, so we'll spend a large amount of money, we'll do a very careful structural survey, we'll build a model and we'll see exactly what's going to happen. Or they could say, here's some place up north, they'll say, well, yeah, let's see if it floods or not. Maybe, here's a 10-minute model that we could just use for that. Okay? So there's either a bespoke model, or there's a general sort of like lightweight model that you can use. So the lightweight model is just there, ready for you to use. Okay, so I mean, I said it in a slightly dismissive way, but lightweight models are clearly very useful because you can use them in many, many places. You don't need to do all of the tuning, but of course they have different principles attached to them. Anyway, so FUSE allows the creation of many different models, and we'll talk a bit about how they're all set up. Each model is very quick to run. So there's an issue about choosing which form in any particular catchment to use, and we'll ignore that for this talk. We'll suppose that we've picked one. So here's the original paper where FUSE came up. Okay, and the reason that I love it so much is that at first it was implemented in Fortran, and then it was implemented in R. So here's a nice, if you're looking for interesting problems, so for example, to give your students, we often run this as a student project because there's some nice data on rainfall and runoff. It's easy to understand, but it's quite challenging to model, and it's a nice R program, which is easy to do. And we were in the NERC Racer project. Serge was, where's Serge? Yeah, involved in this, yes, and it was one of our exemplars. Okay. So here's the model. Basically, it's a box model with some differential equations pushing things around. There's an upper layer, there's a lower layer. Rain comes in, evapotranspiration goes out, and there's runoff, interflow, and percolation. Each layer itself may have boxes. So there's the upper layer in this model has a tension box, and some of it can go down into a free box. And then the lower layer can have many adventures. In our model, it's quite simple. Okay, so to run FUSE, you have to choose your boxes, and then you have a time series of rainfall. Usually this is taken, although in our examples it was taken from rainfall gauges, then keyed over the region. Then there's a time series of evapotranspiration using the Penman-Monteith equation, which is another of these magic things that you sort of calculates evapotranspiration from a bunch of things. Basically, as far as I can see, it tells day from night and winter from summer, and it does that very well. And then you need to choose the model structure and the parameters. When you have that, you go, and then the model will do things. So you need a catchment, you need a place for this to happen. So what we're going to talk about is a particular catchment in Pontbren. The data is available if you go to the website. Okay, and so you can see, if you really squint, the white triangles are the rain gauges, and there are stream flow gauges in black at various points. Okay. So just as an example, there's a particular period between September and November which will be for this illustration. So rainfall is the black line, and it drives stream flow discharge the red line over the time period. And you can see basically that when rainfall is high, then discharge is going to be high. Yeah? So it's a bivariate time series. The first one is driven by whatever drives rain. The second one is driven by rainfall. What gives it the slightly complex structure is that it has a certain amount of memory. When there's a lot of rain, the underground becomes like more saturated, so there is more runoff. So effectively what these models are meant to be doing is it's kind of like a time series built in with memory, if you think of it that way. And so exactly fitting it is an interesting job. So can the models do this? So again, here's red line is observed discharge. Here's a model one at a fairly good parameter choice, blue, and a fairly bad one, green was not a very good parameter choice. Yep. So you can see that different parameter choices do better or worse jobs of matching, and the notion that they can match, it can catch broad features is not a crazy thing to pursue. Okay, so let's now step back a bit and think about notation and how we're going to do this. So the simulator, it takes as inputs x, these are the properties, it gives outputs a vector fx, system behavior, and often we have a vector z of observations, like the observed flow. Typically, in our case, the simulator isn't expensive to run. Typically, the simulator will be, so anything we do is going to require us to overcome the expense of running the simulator. So we construct an expression of our uncertainty about the value of f of x for each choice x for which we have not evaluated the simulator. So people have different terms for things. I tend to call that an emulator for f. It's an emulator if it describes my uncertainty for this. Okay? So unlike the simulator, the emulator is fast to evaluate, so we can, every time we wanted to use the simulator, we can use the emulator, and because it's an uncertainty statement, we can remind ourselves about how uncertain we are that we've done the right thing. Okay? So now I was thinking by now, when I first wrote this talk, that I would be somewhere in the middle, and so you'd have seen loads and loads of emulators. I think all through, well, I've got no idea what you're going to see during the week, but I'm guessing that a lot of people will emulate things. Okay, so in the Bayes linear case, we just want means, variances, and covariances. In the full Bayes, we would want a full probability distribution. So, but many emulators, certainly the ones that we build, tend to be effectively divided into two components. Okay, so I take a particular output, like, for example, the stream flow at a particular time. Okay? And so the inputs are the parameters into my box model. So, well, let's just put them all up. There we go. Okay, so I divide it into a systematic part, for example, a polynomial in the inputs. Yeah? And where I have to choose the polynomial terms, and I have to estimate the polynomial coefficients, and then I have a residual. Just for the one person who hasn't seen this, so here's x, here's f of x, so f of x wombles around like that. Okay, so we fit a curve through there. So that would be, if you like, my my systematic part, and I call that global because wherever I am in x space sort of tells me something about the form of this this line here. Everywhere the line will get it wrong, and because the function is continuous, the error is going to be continuous. So if I get it wrong a certain amount here, and I move along a bit, I will get it wrong by a similar amount. So therefore, the residual function is a process which has a correlation. So a high correlation means that errors at one point are replicated quite far along the line. Very small correlation length basically means that it wobbles quite quickly around the line. I call that local variation because the only way you can find out about what the value is here for you is by getting near, by putting points in close. Now, different people put different emphases in this. Okay, so I haven't got a slide on fitting emulators, which maybe I should have done, but you can see that it's a stats problem. You put in you choose a bunch of x's to run it, your simulator at. You calculate f of x for this. Okay, yeah. So you have your input line is a bunch of x's and outputs of the f's, and then you use your favorite statistical matching program. If you can actually get access to the equations, obviously, as we saw in the first talk, there are much more sophisticated things you can do. Typically, for the examples we've looked at, that's not going to happen. So people put different amounts of effort into these two different components. A lot of people put very simple mean functions and put a lot of care into the local fit. I tend to put as much effort as I can into the global, extract that, and then try and fit using as simple methods as I can the local. So all I'm saying, I mean, I suggest to you, if you're finding problems doing it, that the notion of putting a lot of care into the global surface can actually pay big dividends, as much as anything, because the global surface allows you to do many things. If I can get to there, we'll see what they are. Yeah. Okay, so how about internal discrepancy? So we take a particular choice X of inputs. What I said is you can imagine a series of perturbations we can make. So here A1 to AN could be perturbations. Yeah. Now, it's two slightly technical slides, but they'll go away again very soon. Okay. If I have a series of perturbations, okay, then I can treat these as what's called second order exchangeable. So they have, so my expectation for these is the same, my variance is the same, my covariance between any pair is the same. Okay, then there is a second order exchangeability representation theorem. It's described in detail in the book, which says that I can basically treat the f of x's that I see as a common underlying mean plus a residual, where the residuals have zero mean, the same variance, and are uncorrelated. And so it's the residuals that I want. So so I would like to just get the residuals by just finding out what they are. If I don't know what they are, then I need to know what m of x is. So the simple cheat is just to substitute in f of x at the default value. That worked pretty well for fuse. The more if you don't want to do that, again, the book will tell you in much more detail how to do this more carefully. So that means that I can actually access the R's, and then I do a second order exchangeability representation for the R's when I square them, and the mean for that is the variance, is the discrepancy variance. So this whole slide here is simply to say that there are good Bayes linear calculations that you can do to get to what v of x, to estimate sort of the v of x for a particular x. And then it says, once I can estimate v of x at a particular choice of x, I can do a series of x's where I estimate, and then I emulate v of x over everything. And again, the calculations for that are straightforward. I mean, there's a bit of detail to them, but there we go. Okay. So I take a particular choice of x, I run a bunch of repeats, from that I learn about the variance of v of x, and then I do that for a series of these things, and then I emulate over the whole surface, and because I've done a proper Bayes linear calculation, I've carried forward the uncertainty everywhere. Okay? So let's say a little bit about fuse. Okay, so fuse is actually quite hard to emulate point-wise. So what we did is we started by looking at the log of the maximum discharge over one of the rainfall events. And so we have a bunch of parameters which describe what happens in all the boxes. We're trying to use these, find functions of the parameters which get close to the maximum log discharge. And so because the model was cheap, we ran it at 1,000 points. Had we not been cheap, we could have done it for about 50 points. I'm sure it would have been fine. We get, we used a quadratic fit, and we get a pretty good R squared there. So we're sort of happy with that. Okay. We then used a Gaussian correlation on the residual, okay, basically by a bit of trial and error, and we removed some of the parameters from the emulator altogether because they weren't doing much work. So there's a little nugget of residual variance, and we did some diagnostic testing. We chose some different points and checked that we were within error. Okay. So now internal discrepancy experiments. Okay, we have evapotranspiration. So that is pretty rough. So we varied it. Okay, we could have done more on this, but we just said let's just perturb it in a correlated way across time. We correlate. The model parameters that we treat as fixed, clearly they are actually slowly changing over time. So we put in some. The model was written in such a way that it was quite straightforward to add some discrepancy to those. The rainfall forcing function is a bit more detailed, but it's easy to understand. The rainfall gauges have measurement errors themselves. The creasing has error, so we basically built in a discrepancy, a different way. So what was presented was the mean of a process which had a whole bunch of uncertainties like this. So our perturbations were samples with respecting that error structure. Okay, so we could do each one of them individually, which is quite interesting, but we want to do them together. So we took 300 perturbations of each one of these things, which we combined to have 300 joint perturbations. We chose 50 input settings to run the model. Again, it's interesting how many you do of each. That's a good, interesting design question. You run the model at each input parameter for each of the 300 perturbations, which leads you to a standard deviation for the influence of the perturbations. And so I said we emulate, but initially we just took the maximum because that was fine for what we wanted. And we'll see later on we did something a bit more careful. So we have a bunch of variances here. Here was our emulator variance. That was a nugget effect for the things that we're not putting in the emulator. Here was our max internal discrepancy, the stream flow gauge measurement error, and then our external discrepancy was that. Okay, so these are all the uncertainties that go into this. Okay, so now what are we going to do? Okay, well, I'm always hooked on this history matching thing. So we're going to, so we could calibrate the model at this point, try and learn what the true values of the parameters are, but we may not believe a true input value for the model. I certainly don't here. There may be no good choices of a parameter, and probabilistic calculations can be very difficult and non-robust. Okay? So history matching is, I told you what it is before. You're trying to find that collection of input choices such that if you run the model at those choices, you will get a match to what you actually observed historically, consistent with all the errors that you actually have. Okay? Now, again, if you might just want to do that, that might be fine for purpose, or you might really want to calibrate. Even if you want to calibrate, I suggest you first do a history match, so you reduce your parameter space to a small, well-behaved subset, and then many of the problems you have with calibration will disappear. Okay? So we use an implausibility measure. There's one. Okay, there are many different ways you can do this. So Z is what I observe. Expected value of fh of x is my expectation out of my emulator for that output. I look at it divided by the variance, which will be the sum of all the uncertainty errors sort of in the problem. And we can either do it on a single output at a time, we can combine them multivariately. There are many ways we can do this. And so we get rid of points. So the point about history matching is you're not trying to find the good fits, you're trying to identify the bad fits and remove them. So all the bad fits go. What you then do is you make simulator runs again in the subregion, you refit the emulator over the subregion, and you then emulate extra things that you couldn't emulate before, and you repeat. And you keep repeating this process. Okay, so it's an iterative global search. Okay? So again, when I realized I was at the beginning, I thought perhaps I should do a picture for this. Again, I thank Ian Vernon, whose pictures have traveled the world explaining this. Okay? So here's a function, x goes along, there's a function going up. So here's an emulator for it. The blue line's the expectation, the red lines are uncertainty bounds. Okay, and so the emulator's fast. Okay, so there we are. So here's an observation that we could make, and with its uncertainty bounds, and there we see a history match. The green is a history match, the red is all the points that didn't match, so they're implausible, so we get rid of them. Now, that's the first wave. So we now perform a second wave. So we now know, if we go back, we don't care about the red space anymore. We only care about the green space. So there we are, we jump in, okay, into the green space, we reduce, we put extra runs in there, and now the emulator is more accurate, and we get our, effectively, the green space really only reflects a measurement error at this point. So the key thing that makes history matching work, which is why I recommend it, is you only need accurate emulation of the simulator in the region close to the output match. Further, there are some outputs for your model that you may not be able to get initially at all. Once you cut the space, then later on you can bring these in. Okay, so as a practical method for handling complex functions, to me it's just it's very practical, and it's a bit of an art form, but it gives you a lot of potential for doing problems which it would be really hard to do a one-shot technical sort of analysis for. So here's fuse. So we've done this history match. So each point on the heat map was generated by fixing an x1, and which was two of the variables. It tells you what they are, and varying the other parameters on the grid, and calculating the proportions which will be rejected. Basically, the redder area is basically rejecting, and in the whiter area, most points are accepted. So we do that. We now generate a new collection in the part that we've kept. Okay, we build a second emulator, which is a better fit, because I mean, one reason you should imagine it is a function is complicated. You cut off some of the wiggly bits, it becomes smoother, generally. So we now do a second set of runs of the to get our internal discrepancies. We now build an emulator for it. Emulators for internal discrepancy tend to be quite easy to build because that's quite a smooth function. We get a reasonably good R squared for that. Therefore, when we do our history matching, we use our emulator to understand discrepancy, and that is much more efficient than taking the maximum, and it explains that there. And so there we are after the second match. Okay, and so we're starting to sort of ready starting to go on the march. We then do it one more time. We do another internal discrepancy assessment, and I told you we were looking at the log max. Before we couldn't get the total rainfall very well, it just emulated badly, but now it emulates quite well, so we put that in, and we further refine the region, and we could continue by introducing further features to the output. Okay, so let me say a quick thing about forecasting. Okay, so I said before along here that you wanted the nice curve was easier to forecast than the bad curve because we had credibility for it. But anyway, you do forecast it, and so my comment about forecasting is that right at the end, okay, you now want to take y into the future, okay, and so you have historical observations, and effectively what I've told you, you have to unscramble it quite carefully, is what the joint distribution between the ZH in the past and y in the future is. And what our emulation has done basically has given us that joint. Okay, so let me, because I want to get on to the second example, so let's quickly talk about this. So here's doing a small example of forecasting using fuse. So here's our historical max and historical sum. We want to forecast the future max and the future sum. This is the correlation for the discrepancy. You can see that within the past they're highly correlated, obviously. In the future they're highly correlated. You can also see that the past and the future are highly correlated. So if you left that out, your forecast would not be very good. And there's a comment here about doing that. Okay. Fine, so let me now quickly move on to where I want to get to for our second example. So let me go back to a picture I've shown so many times, and people are always happy with this. We start with model evaluations and actual system and system observations. So the notion that we were using is that basically there's a model, you could stick in the actual system input, you could stick in discrepancy, and you could stick in measurement error, and our job is to analyze that picture. Okay? Now people are happy with it because it's already, well, they're not that happy because it's a whole bunch of things that they hadn't thought about before, but effectively it's a representation. But you can see again in this representation that f of x star separates everything out. It's like there is a system input, but what do we mean by that? Okay, so let me now have one slide on effectively what I think is the better way to think about this. So why should we think there's an x star effectively that splits things up like that? Okay. Okay. So the question is, what does a simulator f really tell us about the physical system? Okay. So why, when we've done a bunch of runs of f, have we learned about real system y? Okay. And then of course there's a question about if we had a bunch of simulators, how would we put them together? Okay? So I tend to view these things really, okay, they are abstractions and simplifications of real physical quantities and processes because of the approximations we've made. So there are approximations to something, okay? There are approximations to a more realistic simulator, F star. For example, in our reservoir model, we're on a grid, which is a fairly coarse grid. We are approximating effectively a continuous system. Okay? So in that continuous system, it will still have limitations. I'm still busy working Darcy's laws, which are an approximation. But because it's sufficiently realistic, we could put like real system properties in, and then if we, okay, so we consider our inputs X and S, simulator F, as abstractions of real physical quantities and processes to a much more realistic simulator F star, for which real physical X star is the best input. And what do I mean by the best input here is that F star of X star would exhaust all the information that I have from this line of reasoning. Okay. So Y minus F star X star would be independent of X star and F star. In other words, the F star would be good enough, okay, that if I could only know what X star was as well, then F star of X star would be my judgment for Y. Doesn't mean it would be true Y, but it would mean, just like if I take, in general, a posterior judgment about something, okay, then the difference between my judgment and real, I have to judge as independent of the things I put into it. Otherwise, I would have modified my judgment. Okay? So I tend to call that the reified simulator, from the word reify, to treat an abstract concept as if it was real. Okay? So the reifying principle is that the reason that F is informative for Y is because F is informative for F star, and F star and X star is informative for Y. And if I had a bunch of simulators, they'd all be informative for F star. So it's interesting, well, I don't know whether this is a good term or not. I tend to view everybody who uses models as, reifying is normally considered to be a mistake. Yeah? You took a model and you wrongly treated it as if it was real, and therefore you did bad things. Okay? So what I take the act of reification is to turn it in, what would you have to do to make it not a mistake? Okay, and this is the argument. Okay? So there we are. So this was a picture I told you before, but that's a picture that I really would like you to hold in your mind. Okay? Okay? So now this is where I'm so happy to be a Bayes linear person, because I just emulate further down the stream, and then if I had code before that history matched it, forecasted everything, I just use the same code, and I just use this picture to change my uncertainty specification. Okay. So how am I going to do this? Okay. So the simplest way, and one of the reasons I like setting up a global feature function that has a lot of sort of power to it, is to say that probably what's going to happen here, as I move and get more careful, is that global function will change. Certainly from my reservoir example, it was very clear that when I coarsened the simulator, I would get the same terms in my global function. The coefficients would change. My natural thought is that if I refined it, okay, again I would keep the same quantities, but again the coefficients would change. And the magnitude of those changes is really how far I believe I am from an inference which I could apply to the real world. Okay? So I call that direct verification. I just look at my model, I look at the terms in the model and think, how much would I want to change them? Now let me quickly go on and say that obviously I might do better than that. Is what I call structural verification, is where I am a bit more thoughtful. Okay, so I can imagine generalizations which would give me better models. Okay, I can't build them more. Well, I could go ahead and build it, but I'm just thinking about it. Okay, so what I might then do is I might then build my verification in two parts. Firstly, I carefully think about my beliefs about what would happen were I to build. Usually this will correspond to extra processes. Okay, if I put extra processes in, I would get a rather more elaborate emulator, and then I do a direct verification of that. Okay? So very quickly, let me give an example. Okay, this is thermohaline circulation. Okay, So you can see that the heat is carried around the globe. It sort of starts, it gets hot, gets up to about to the UK and suddenly becomes very cold. That's heat and salt. Things become, it's cold and salty up there, so the water sinks, and it sort of does a sort of a circuit. And of course, it's quite an interesting topic because various simple models suggest that, for example, that some of the mechanisms that create this turning could turn off. For example, that the water in around the Atlantic, if the ice caps melt, it becomes a lot more diffuse. The forces that create the cycle could slow down. Here's a statement from The Guardian, which says the chances of the Gulf Stream shutting down are now thought to be greater than 50%. Okay, so what were the models that this was based on? It was based on things like, if you think that, this is a 4-box model of the Atlantic. There's a south, there's a north, and there's the tropics, and water just carries on around. Okay, it's driven by temperature and salinity. So changing temperature patterns and precipitation patterns alter the temperature and salinity characteristics. This could lead to, in principle, to thermohaline shutdown. So it's this the overturning that is the driver of this, and in this model it's driven by the differences between the south and the north box. Okay, and so the state vector is driving this. Okay, and the state vector is temperature and salinity in each box. Okay, so large values of F1, the freshwater forcing that's reallocating there, make the South Atlantic more salty, reduce M, and we're interested in the analysis that was involved was interested in the value of F1 at which equilibrium overturning collapses to 0. That's F1 crit, and the argument is that if F1 is greater than F1 crit, then arguably those changes will be irreversible. Once it collapses, there is nothing to start it up again. And the value was considered to be of interest because the current value of F1, certainly at the time of the analysis, was considered to be close to F1 crit. So when you talk about things about rapid climate change, for the rapid climate program that was funded, it was on arguments like this. Okay, so we have a bunch of model parameters, a bunch of model outputs. Okay, and we want to reify this. Okay, so obviously, you should only reify within what the model is trying to do. Obviously, it misses many things, but it's meant to capture a broad level of what's happening. And people who advocate this think that the very detailed models get to the point where they miss this because they're analysing processes at the wrong level. But here's what, so Jonty Rougier sort of thought about this, and he said, well, here's an obvious one to add on. It is not the case that all the water goes around here. Some of it leaves out to other oceans, and about the same amount comes back. Okay, so we'll give you a reference for this. So you can now imagine building this model. You can imagine the effects that this would have. So this is about adding extra processes. It's not something on the model itself. It's building processes on the model. So effectively, this is what we did. Okay. So we now have to match to data. Let me quickly show, can you really match this to what's happening in the real oceans? Not really, because it's a very high level of aggregation. So we matched it to Climber, which was another model which itself had been matched to the ocean. So let me just jump all this. Okay, so we build an emulator for F1 crit itself, which is an interesting quantity. It comes out of, which is quite expensive to evaluate. We have a bunch of differences. Let me not talk about them in any great detail, but basically we need to think about the difference between f of x and f dash of x, which is the 6-box model, and then between f dash of x and f star, which would be what we would do effectively to further verify it, and then between f star and real climate. And so just to get to the answers, so let me get to where I can finish. So the current value of F1 from Climber was 0.014. So from 30 evaluations of F plus the verified statistical modelling that we did, we got F1 crit to be 0.085. Okay, so F1 crit's bigger, but it has a lot of uncertainty on it, so it could in fact be smaller. Using the Climber 2 data, we then effectively, now we're forecasting, but we're not forecasting across time, we're forecasting another output. Okay, and so we did that, and so we forecast F1 crit to be higher, but with smaller variance. Okay, so I think we were a bit safer having done this. Okay, and in terms of who believes what, I asked John T at the end, did he more or less believe this? And he said more or less he did. These were his judgments at the end. Okay. I'm neutral on this, but anyway, yep. Now, again, a general point here, as a subject that is really important, is model design. Should you build that extra model? Okay, because after all, we're just speculating here. Okay, so effectively, we can now make an estimate about, supposing we actually had access to that model, how much would it actually reduce our uncertainty? And again, we can do a calculation. It would reduce our uncertainty by around 10%. It certainly would reduce it much more than doing a lot more runs and analysis of the 4-box model itself. So there is a subject here of, it's not just analysing people's models, it's directing people and helping them. Verification helps you to think about your uncertainty related to the world, but also drives you to thinking about how you could reduce that uncertainty. So our conclusions, that there's internal discrepancy modelling I talked about, reified modelling I talked about, use of surrogate models for each, so it provides a logical rationale for linking models to systems. It provides a structural modelling approach for quantifying discrepancies using whatever physical intuitions we have. If you have, I didn't talk about this, but if you have several simulators, they can all come into our verification, and I don't know another way of doing it. Okay? And here's 3 references. The first one is to the flood modelling and internal discrepancy. The second one is to the ocean model and external discrepancy. And I always put that one up just to remind people that there are reasons for being a subjective Bayesian. Thank you very much.
So it's very interesting ideas that you're presenting. I'm a little unclear on what kind of assumptions you're making on the model that you're trying to emulate. You talked about the linear equations at the beginning. I don't think you mean to restrict it to linear problems. How about multimodal problems? Can you do that, or does it need to be convex?
Well, first, the equations are general, the calculations are general. The question about when they are, as I said, the hard part is not actually doing the calculations, but deciding sort of the right way to use them. For example, if I do think the problem is multimodal, I might first want to start at the modes, and I might want to divide sort of my function up sort of by modes. And again, so it depends. If I'm thinking about the output, I mean, that's why I would fit, for example, like quadratic or cubic terms with interactions. Yeah, so the modes themselves are fine. It's, and again, if I'm thinking that my fits could be effectively that there could be different ranges of parameter choices which could be well separated, which could give fits, then I would separately run my emulator in space 1 and separately run my emulator in space 2. So there are, I mean, things don't automatically work for you. You need to be thoughtful, but I'm not sure I answered your question or not, but...
Yeah, I have a part 2 here, which is related to what you just said, which is, it seems to me you're doing a lot of evaluations of your function, and the fused model that you described is, it's a fraction of a second to do that. But I work a lot with, real models that are much more complicated than that, and it can take minutes, it can take hours.
Yeah. Oh, well, the reason
so what you should have, wait. So what you should have is an assessment of just how many evaluations you need to do to do the procedure that you talked about. It seemed like it was a very large number, but maybe not. But it's just, I'm suggesting, especially if you then have to repeat it in the different modes of your space, which you have a lot of modes if you have a high-dimensional problem.
Yeah, okay, so let's jump back to here. Okay, so the models that we talked about are things like galaxy formation, okay, which those galaxy models take sort of days to run. For the climate change, we were working with, I mean, my climate change examples aren't really the 4-box model, they are with things like sort of larger ones. The energy planning models are very slow to run, they have a huge optimization step every time you run per minute. The disease modeling is very high dimensional, we are looking at different interventions over big periods of time. The oil reservoir models take hours to days to run, Okay, so we are talking about methodology that is designed for slow models. So when I showed you,
how many times would you have to run those?
yeah?
How many, do you have to run those thousands of
No,
times?
no.
That's why I don't understand.
No, the reason I did for the flood model 1,000 times was just because we could. So it seemed silly not to do that, because I was trying to show you the potential, that these calculations were reasonable to do. But effectively, as I said, obviously the more you can run a model, the better. Here, point one. Point two is that, for example, with the oil reservoir models, to actually capture the structure, you need to again use physical understanding. For example, early time just depends on local geology of the reservoir, so you can do a fairly small number of runs can fix that, and then so you have to be pragmatic about how you do things. Thirdly, a lot of building emulators does actually rely on expert judgment as well. Fourthly, in fact, and this is the thing I will be talking about at the next workshop, one of the key things if you have a slow model is you look at fast approximations to the slow model. You build your emulator on the fast model that you can run more times, because that will basically, the thing that really takes you the large number of runs effectively is to work out in that G of X I did, not what the coefficients are, but what the terms should be. So we create fast approximations, which we then which we learn about the form of the G model. Yep, okay. And again, just like I told you that when you build your model, you should make it easy to do internal discrepancy experiments. When we're working with modelers, we say, look, if you want us to be able to emulate your model, give us ways to create fast approximations so that we can actually build informed priors for doing this. So yeah, obviously expensive slow models are a challenge, but we have a variety of ways of addressing that challenge. And I don't know an alternative way of doing this.
Okay, I think in the interest of keeping the time, we thank again Michael and